So welcome back. In this lecture, we're going to discuss Bayesian networks as classifiers. And classification is probably the most common task in machine learning. And it would be interesting to understand how we can use Bayesian network as classifiers too. But we need to understand if they're going to be effective and efficient classifiers and how we can compare them to other classifiers. You're going to see that a very simple classification system that we have in machine learning knows that naive Bayes classifier is actually a Bayesian network. And we know that the naive Bayes make very strong assumptions about the dependence of attributes. And I'm going to see how we can extend those models in order to make those assumptions a little bit weaker. So yeah, let's get started. So now you understand a little bit more about Bayesian networks, and probably you haven't noticed the difference between making a model with a Bayesian network or a probabilistic graphical model compared with the models that we create in machine learning. So I guess first thing that is very clear is that the models we create with Bayesian networks, they are understandable. So it's part of what we call the explainable AI. And it's very important part of the modeling process to understand the domain. I know that we can learn the graph from data, and there are techniques for doing that, but frequently we want to understand the problem, model the problem in a reasonable way in order that the model will be a good approximation for the real problem. You probably have noticed that when we create a model for machine learning, the model is very task specific. So we create a model for classification or regression, and the model will only do that. We only classify the class variable, or we only predicted the target variable for regression. But in the case of Bayesian networks, we can have different queries, and we can have different variables as query variable, and we can have different variables or evidence. And we can use all that information in different situations. For instance, we want to make a diagnosis for a disease. We have a certain exams that were done by the patient, and we can ask what's the probability of the disease given the exams that we have right now. And if this probability is very small, we can ask the Bayesian network how would be that the probability if we increase and have as evidence more exams. So we can make different what if scenarios and different analysis doing that. But in this lecture, we're going to discuss Bayesian networks as classifiers. So we're going to split all variables that we have for a certain domain, for a certain data set, into two groups. There are attributes and the class variable. And we will try to predict the class variable based on the information that we have for the attributes. I think that's going to be an interesting exercise because we will be able to discuss some topics that we have covered before, like independence, and also some other topics that we're going to see in the future, like learning and inference. And it will be also an opportunity for discussing naive Bayes and a few extensions. And we see that these are very simple Bayesian networks. So in order to make this discussion more concrete, let's take one example. And in this figure here, we have a Bayesian network for the diagnosis of breast cancer. So this diagnosis is going to be based on one exam that's called a mammography. And a mammography is an imaging exam. So basically, we will observe the breast cancer, and it will appear to us as a mass, right, in the image that has a certain size, a certain shape, has a margin, that is the border between the nodule and the remaining of the breast, and we can put together with other information, and also, for instance, the location of the person, the age of the patient, and so on. So we'll have basically two sets of variables. We have the class variable that is going to be a single variable, that's going to be just a variable for breast cancer that we'll call B, and we have the other variables that will be all attributes. And those other variables, the attributes, we're going to use them as evidence for the Bayesian network. So we're going to observe them and use this information as evidence in order to compute the probability of B. And we can call this evidence as E. I'm going to write it here. It's going to be E. Let me try to make it in boldface. It's going to be E in boldface, representing all the pieces of evidence that we have. So it can be more than one attribute. Usually it's going to be values for all possible attributes but the class. So this is a typical classification problem that we have in machine learning. So we give one example that you want to classify, and this example has all the values for all features but the class, and we want to compute which is the most probable class. So we can look at some relevant aspects for these Bayesian networks as classifiers, and the first of them is going to be the type of query. So it's very clear that we are interested in the probability of B given the evidence E, right? So you want to compute, so imagine that B can have several different values. Each value is a class, and I want to know which of those classes is the one that is the most likely. And this is the one that we're going to give you as response. So the type of query that we're going to compute in the end is one MPE query, because the class information is more important in a classification problem than the probability itself. So frequently we are looking for which is the class that I should assign to this new example. Sometimes we are also interested in the probability of that class, but ultimately is the class the information that we are looking for. So the MPE query is the query that's gonna give us the most likely assignment for B given the evidence. And the second important aspect are the independence assumptions. And we want to understand which attributes are independent of the class given other attributes. That's going to be very important to us to understand that, because we're going to understand some assumptions of this model. Possibly, we can have some attributes that are de-separated of the class given other attributes. And in the end, those attributes will never contribute to change this probability of the class given the evidence, because they are independent of the class. So we want to understand that who are those attributes that are not contributing to the classification. And also learn structure and parameters. And in this specific case here, I'm showing you a Bayesian network that was created based on an interview with experts. But in the case that we want to create that Bayesian network from data, what are the possibilities that we can have for classification in particular? And we see a few possibilities in this lecture and a few more in the future lectures. Okay, so let's talk a little bit more about the query that we want to make when we are working with Bayesian networks as classifiers. As was saying in the previous slide, so we are interested in computing the probability of B, that is our query, the breast cancer, given the evidence E. Right? And the evidence E is basically all the information that we have about all the attributes that compose the example that we want to classify. And if we compute this B given E, we're going to see that this is going to be a small table. For this problem in particular, we have just three possible values for this class attribute. So we say we have three possible classes. It's null, in situ, and invasive. So when we compute this probability of B given E, what we have is a small table with three entries. So it's going to be two columns, one for B and the other one for B, probability of B given E. And we have just three entries here. One is for null, one is for in situ, and one for invasive, right? And that is basically the output of our query. And for each of these three entries, we're going to have a probability. As the probability of B given E is a probability distribution, they will sum to 1. So it's going to be like 0.7, 0.2, and 0.1. As I was saying, frequently when we have a classification problem, we are not interested ultimately in the probabilities, but in the classes. So we take the class that has the highest probability and we give that information as output of our classifier. In this case, the output will be the class null. So if we have an observation for all the possible variables, but of course B, we call this query the MPE, that stands for the most probable explanation. So as the name suggests, what we are interested in is to find the explanation, that is the value of B that has the highest probability. It's interesting to note that if we have a missing data into the test cases, so imagine that we have to classify one case that has missing data, that would be dealt by the Bayesian network in a very natural way. So what we would do, we would instantiation, observe some of the attributes. The other attributes that we cannot observe, that we did not observe, we don't have it in the test case, we don't set it as evidence, and we run a query that is very similar to MPE, that's called the map query. So the map stands for the maximum a posteriori, and it's very similar to MPE, but it allows us to have some nodes that are not observed, right? And we will have to make a little bit more computation because we have to eliminate those nodes by doing a summation process. And we will see how we do that in when we discuss inference. And also there will be a lecture that will be specific to discuss algorithms for MPE and map inference. Okay, just to emphasize the difference between MPE and map. So we have a Bayesian network like this, and it has a set of variables X. So these are all the variables occurring in the network, including the query and the attributes. For the MPE, we have just two sets of variables. So X is going to be split into two subsets. One is Q, the query variable or query variables. That's going to be united with the variables that are in the evidence. So there are these two sets, right? They are mutually exclusive, and when we put those two sets together, we have all the variables that belong to the network. For the map, it's going to be three sets. One, so we have X, it's going to be equal to 1, it's going to be the query. The other one is going to be the evidence, right? This all boldface. And there is a third one that is going to be the variables that we did not observe. I will call these the latent variables, L, right? These variables we need to eliminate in the middle of the inference process in order to get the response for the map query. But you don't need to worry too much now about the map query, because we're going to see in the next lecture how we're going to make inference with Bayesian networks, and we're going to see how we eliminate those variables. For now, we're going to work with the MPE queries. So we're going to assume that we have values for all the attributes. And that is the most common case in classification, where we have one complete example that we want to classify and determine what is the most likely classification. Let's take a look at the next slide. Okay, so we decided to work with these MPE queries, so we have complete data. So we're going to observe values for all attributes. So imagine this Bayesian network, and we want to classify this breast cancer node here, and we're going to observe everything. So imagine that happening, right? So I'm painting those nodes representing that we are observing them. But we know from this operation that when we have those nodes observed, it's very likely that we can block the influence between one node and the other. So let's use one example. So we have this breast cancer here, and we have size. right? And we have this path connecting breast cancer and size. So it's going to be a chain, but we observed mass here, right? So size will not be able to influence the breast cancer because of the mass. So we have this feeling that possibly some nodes will be independent of breast cancer, our class attribute, given other nodes that were observed. So it's important to understand which are the variables that will influence the classification and which are the variables that will not influence the classification. And the central concept for us to understand which variables will influence the class attribute and which ones will not influence is called the Markov blanket. So we have the variable x here. We expect to have parents. I will draw 2, but we can have more or less. We will have children. I will draw another 2 here, but we can have more. And we have the spouses. So the spouses are the parents of the children of x, right? And this is the Markov blanket. We say that if we observe the variables in the Markov blanket, we isolate x from all the remaining variables that we have in the graph. So let's try to understand why that happens, right? So here, by this operation, if we have more nodes here on the top, it will not influence x because it's going to be a causal chain and the parents are going to block this influence. The children, we may have more descendants of x, but because here we have a causal chain that's going down here and we have observed the children of x, it will block the influence. And also very important is to observe the spouses of x, because as we have observed the children and we have this convergent node here, the spouses can influence x, right? So understand that this is the exception that for the d-separation algorithm, and this is going to be not blocked if we have the convergent node observed. So yeah, it should be an interesting exercise here to look at this more complex graph and try to identify what's going to be the Markov blanket. Okay, so let me first erase this. Otherwise it's going to be too much confusing. And we have the class variable, breast cancer, our x here, and we have the parents of x, age and location. And that's all the parents. Let's look at the children of x. We're going to have microcalcification, skin retract, nipple, and also architectural distortion, mass, right? These are the children of x, and we also look at the spouses of x. And the spouses of x, remind, they are the parents of the children of x. So we have this guy, breast density. We also have this tissue here, also parent of children of x. And I think that's all. All right, and the remaining variables are not part of the Markov blanket of x. So we have size, shape, margin, and speculation. So these 4 variables will not influence the classification of x. They will be blocked by the remaining variables. So we can look at this from 2 different standpoints. One, we can find the literature. Some authors mention that it's a kind of a feature selection. So the model is selecting which features will be included, will participate of the classification, which will not. But it's also, we can look at this as a sort of a limitation of the model, because the model is not using all the information that we have available in order to have the final classification. But when we look at these, we are looking at the variables that contribute and the variables that do not contribute to the classification. But we should look a little bit more careful to see if all the probability distributions that we have inside these nodes are going to be used for calculating the final probabilities for the query. So we're going to see in the next slide that in fact, all those variables contribute to the classification, but not all probabilities that we have inside the nodes, the conditional probability tables, will be used in the classification. So let's take a look in the next slide. Okay, so basically this is the same information that we had before, a little bit better organized. Let's take a look at that simpler example. I think that it will help us to understand this idea a little bit better. So we can use this very simple toy Bayesian network in order to get a better understanding. And in this network, we have the variables winter, sprinkler, rain, wet grass, and slippery road. And we can think that the winter will interfere with the rainy season, and also is more likely that you're going to use the sprinkler in the summer when it's hotter than the winter. And both variables, sprinkler and rain, is gonna influence if you have a wet grass, and the rain is also make the roads more slippery. And let's think that we're gonna have a query variable sprinkler, right? So the variable is gonna be b. In this case, we need to see what's gonna be the Markov blanket, and in this case, this guy here is a parent. This one here is child, this is spouse, and this slippery road is nothing, so it's going to be outside the Markov blanket. So we expect that these three variables will influence our classification of a sprinkler that can be true or false. So let's suppose now that we're going to make the classification, and that's going to be a very simple case of an MPE inference. So let's suppose that this is our evidence. Remember that we are using the complete case, so we have a instantiation for each variable but b. So in this case, a is going to be true, c is going to be false, d true, and e false. And when you compute the probability of b and see what is the most likely value, is going to be true or false. In order to do that, I think that the simplest thing that we can do is to use the chain rule for the Bayesian networks in order to compute the probability of b and together with the evidence. So we have this probability of b and the evidence, and according to the chain rule for the Bayesian networks, is going to be let's look at the network there. It's going to be P of A because A has no parent. It's going to be P of B, given A because A is the only parent of B. It's going to be probability of D given B and C. So D is this node here. It has the two parents, B and C. So correct. Probability of C given A. So C has one parent, that's A, and probability of C given E. Actually, this is wrong. It's going to be the probability of E given C because C is the parent of E. So, okay, and as we know the instantiation E, we can put that here. So we know that A is true. So A is true here. B, we're going to leave that as a variable, and we check for two possible instantiations. And A is true, D is true as well. So D is true. B variable, not C. So C is going to be false. That's correct. Not C and A. And here is going to be the probability of not E. So E is actually, correct, false, given not C. All right, so we have everything and we need to compute that. So let's take a look at the next slide. Okay, so we can now compute the probability of a B and E, and I'm going to show you later on how we can convert these to the probability of B given E. that it will be what we are mostly interested in, but we're going to show to you that it's just a sort of a normalization step that we can do afterwards. So we can compute the probability of B and E, and we can compute the probability of not B and E, and we're going to see that we can use these two probabilities in order to compute the probability of B given E and the probability of not B given E. It's very simple. It's just a normalization. But let's concentrate now of this probability of B and the evidence E. So use the chain rule, P of A, P of B given A, P of D given B and C, P of C given A, and the P of E given C, right? And we use the instantiation, and we take the values from the table. So the probability of A true is going to be here, 0.6. So this is 0.6. The probability of B given A is going to be from here. It's going to be, so times 0.2 times the probability of D given B and not C is going to come from here. It is 0.9 times the probability of not C given A. It comes from here. 0.2 times the probability of not E given not C comes from here. It's going to be 1. So the result is going to be 0.0216. And we can do now the same calculation for not B and E. Let's do that in the next slide. Okay, and now we do the computation for not B. And we're going to be very similar. We take the chain rule for the Bayesian network, and we compute, I have to fix this. This is EC, this is EC, and this is conditional, but they're going to be very similar, right? So we're going to take P of A, now P of not B given A, because we have the not B instantiation, P of D given not B and not C, P of not C given A, and P of not E given not C. And if we multiply and it's marked here, what are the correct values, we see that the number is smaller than the first one. So our classification is going to be B equal true, because this is the value of maximum probability. And you may ask why we are computing P of B and E. Shouldn't we be computing probability of B given E? Is actually what we are interested, right? So we have the evidence and we want to know what's the probability of B conditional to that evidence. And for classification purposes is actually the same thing, right? So we can see that if we say that probability of B given E is the probability of B and E divided by the probability of E. And we can compute the probability of E by using case analysis. So it's going to be the sum of BE and not B and E. So it's actually these two values here. So what we are doing here is just a normalization. So we sum the two values, and let's call it Z, and we divided this by Z and the second one by Z2. So it's going to just be a normalization. We will not change the rank of the two numbers. All right, so but another piece of information here that's very important is what in fact is making a change or make a difference in order to have these final numbers and decide that B should be equal true. It's the most likely. The value is the value of the highest probability. Look at that here. We have the same term P of A. So we can, cancel this because as we are comparing the two values, it's not going to change anything for us. These two terms here we cannot cancel because one depends on B and the other one is not B. The same thing for here. Here it doesn't matter. It's going to be a constant that being multiplied in both equations, and here also constant. So actually what's making difference is just these two terms here, right? They are the terms where B appear. So these are the conditional probabilities where I have the variable B. So in this case, we are just using the information that we have here and the information that we have here, because these are the tables where B is present. So you may be asking something like, well, it's true that because we saw that the Markov blanket are the relevant variables in order to decide to isolate B from the remaining ones. So what you're showing here is actually saying that the theory is not correct because we are just looking at the nodes B and D. And we say, no, the theory is correct, because if you look here, we see that those conditional probabilities will take into consideration the values of the variables that are into the Markov blanket. So they are important. They will tell us exactly what is the role that we should take from the conditional probability. So we see that the Markov blanket involves A, and A is here. We know that the Markov blanket involves C, C is here, and also D, and D is here, and together with the variable B. But at the end, the probabilities that we are considering are just the ones that involve the variable B, that is the class variable. And when we look at the Bayesian network here, it's very clear that the probability tables that mention the variable B, that is the class variable here, are the tables that are in the node B and also in the children of B, in the case here D. These are the two tables in this example that mention the variable B. So when we make the computation, we should look at the probability tables that mention B, and in this case it will be the probability table stored in the query node and the children of the query node. So in the end we have this, right? So we come back to our more complex breast cancer example, and we look at which variables, which nodes involve a conditional probability table that has the variable B, that is our class variable. We see that is very small number of nodes that have this. There are these nodes here that are marked in green. Okay, so how we can interpret that, right? So it has the feeling that we are not using all the information that we have in the Bayesian network. We are just using a few probabilities in order to make the final decision. Note that this is only valid for the complete case. If you have missing values, so what's going to happen is that some of the missing values may be the variables in the Markov blanket of the node. So in this case, the other variables may influence that variable. So it's very important to understand that we are just discussing the complete case. But even the complete case is very common. So we frequently have a complete case when you are classifying instances in a data set. So it's an important thing to consider. So in some way, Bayesian networks are not using all the probability that we have available, just one subset of them. Some authors say that we are doing a sort of a feature selection and only considering what is most relevant. Other people may say, okay, that's not optimal for classification in the complete case because we are losing too much information. And we're going to see in the next slides are different ways of doing classification. One of them is actually the opposite of this. We're going to take what we call the naive Bayes and going to consider all the nodes together to be influencing the class directly. And in this case, it's going to be, the complete extreme, because all variables will be relevant in order to decide the classification. So let's continue the discussion in the next video.